So, have you ever looked at an AI playing a game like chess or a robot figuring out a maze and just wondered, how? How does it know the perfect move to make? Well, the secret sauce, the real brains behind it all, is a set of rules called the Bellman Optimality Equations. And today, we're going to crack that code together. Here's the plan. First, we'll figure out what optimal even means. Then, we'll learn how to define the best strategy, kind of like creating a treasure map for our AI. After that, we'll get to the main event, the Bellman Optimality Equation itself. We'll even see it in action in a simple game. And then, we'll get a reality check on why this is all harder than it sounds. All right, let's kick things off with our quest for the optimal. You see, in reinforcement learning, we're not just trying to find a good way for our agent to do things. No, that's not enough. We're on a mission to find the one, single, provably best strategy possible. This is really the billion-dollar question, isn't it? It's not about just getting by or doing an okay job. It's about finding perfection. How on earth do you design a system that can look at any situation, no matter how complicated, and know with certainty the single best action to take for the best long-term outcome? Now, to even start answering that, we need a word for the agent's strategy. We call it a policy, and we use the Greek letter pi to represent it. Honestly, just think of a policy as the agent's playbook. It's a simple set of rules that says, if you're in this situation, do this. But here's the thing. Not all playbooks are created equal. A good policy, well, it's fine. It gets the job done, achieves a decent reward. There can be lots of good policies. But then there's the optimal policy. We call that one pi star. And pi star isn't just good, it's the one that squeezes out the absolute maximum possible reward. It's the best of the best. And it's what we're hunting for. So how in the world do we find this elusive pi star? We need a guide. We need a map. So in this next part, we're going to talk about how we create a kind of treasure map for our agent, where every single spot on the map is labeled with its true ultimate value. This map is drawn using something called the optimal state value function, or V star for short. It's a really cool concept. For any given spot on our map, any state S, V star tells you the maximum reward you can possibly get from that point all the way to the end of the game if you play perfectly. It's the best case scenario value of just being in that spot. But knowing how valuable a place is doesn't tell you what to do. You also need to know the value of a move. And that's where the optimal action value function, or Q star, comes in. Q star tells you the value of taking a specific action from a specific state. This is the crucial bit of info the agent needs to actually compare its options and make a decision. Let's make this super simple with a golf example. Okay, so your state is your position on the fairway. Your actions could be using a driver or a putter. The Q star value for use the driver from here is going to be really high, right? Because it gets you way closer to the hole. The Q star for use the putter, not so much. By always just picking the action with the highest Q star value, the agent automatically discovers the best possible strategy. Drive, putt. Simple as that. Okay, so we know we need this value map, this treasure map. But how is it drawn? What are the underlying rules? This brings us to the absolute core of today's explainer, the Bellman Optimality Equation. And here it is. Now, I know it looks a little intense with all the symbols, but I promise you the idea is incredibly simple and kind of elegant, really. All it's saying is that the value of where you are right now, V star of S, is equal to the reward you get for making the single best possible move. You just look one step ahead, see which action leads to the best future, and that's it. The value of your spot is defined by the best place you can get to next. This diagram shows it perfectly. You're at the top, at state S. You have a few possible actions, those black dots. The Bellman equation just says that to figure out the value of S, you have to find the action that leads to the highest possible outcome. That max in the formula, it's literally that moment of choice, right there. And of course, there's a version for Q star, and it's just as clever. It says the value of making a specific move is two things added together: the immediate reward you get right now, plus the value of the best next move you can make from where you land. It's this awesome recursive logic. A great move today is great because it sets you up for another great move tomorrow. Let's look at the diagram for Q star. Here, we've already decided on an action A, so the choice, that max part of the equation, happens one step down the road. After we make our move and land in the new state S prime, we again look at all our options and pick the best one. The agent is always thinking one step ahead.
And this is the magic trick, captured perfectly in this quote. If you actually have this perfect value map, this V-star, you don't need to plan 10 moves ahead like a chess grandmaster. The incredibly hard problem of long-term strategy becomes dead simple. Just look at your immediate options and move to the one with the highest value. It's a game changer.
Okay, enough with the theory. It's time to see how an agent actually uses this treasure map to navigate. We're going to use a classic example called Grid World to see this whole thing in action. Check this out. What you're seeing here is the direct link between the values and the policy. The grid on the left, that's our V-star, our completed treasure map with a value for every single square. And the grid on the right, that's Pi-star, the optimal policy, shown as arrows telling the agent exactly where to go. The policy on the right is created directly from the numbers on the left. So how does it do it? It's so simple it's almost funny. Let's say our agent is on the square with the value 16.0. It just looks around at its neighbors. The square below is worth 14.4. The square to the right is worth 17.8. So, what does it do? It just moves to the square with the higher number. It moves right. This simple, greedy, one-step-ahead choice is the optimal choice because all the long-term thinking is already baked into the values themselves. Now, this probably seems way too easy. And you know what? It kind of is. Which brings us to our last, very important section. The collision between this perfect, elegant theory and the messy, complicated real world. You see, to actually solve the Bellman equation and get these perfect values, we have to make 3 giant assumptions. 1, we need a perfect model of the world. We have to know all the rules. 2, we need basically infinite time and computing power. And 3, the world needs to have what's called the Markov property, which just means all the information you need to make a decision is right in front of you. In the real world, yeah, we almost never have all 3 of those things.
The biggest roadblock is usually the second one, computation. Just to give you a little perspective, this number, 10 to the 20th power, is about how many different board positions there are in the game of backgammon. Trying to calculate V-star for every single one of those states is a monster of a task. For games like chess or Go, the numbers get so big, they're basically meaningless. It's impossible.
So, here's the bottom line. In theory, the Bellman Optimality Equation is our golden ticket to a perfect policy. But in reality, for any problem we actually care about, the world is just too big, and we don't know all the rules. We can't solve it perfectly. And that means we have to settle for something else. We have to find clever ways to approximate the answer. And that leaves us with one last massive question. The Bellman equation gives us the blueprint for perfection, but if we can't actually build it, how do we get close? How do we build agents that can find policies that are good enough to beat the best humans in the world? Well, that's where all the exciting modern stuff like deep reinforcement learning comes into play, and it's the key to how AI is tackling the world's most complex problems.